Recall in our discussion of real gases, we said that we can use the ideal gas law to help us describe the way that real gases behave under certain conditions. So what exactly are these conditions? At low pressures and at high temperatures, we can use the ideal gas law shown here to help us describe and explain the way that our real gases behave. So the pressure times the volume is equal to N times R times T, where N is the number of moles of gas, R is the gas constant, and T is the temperature in kelvins. Now, the reason that we can explain or use the ideal gas law to help explain the behavior of real gases under these conditions is because under these conditions, the distance between two molecules is very high, and we can neglect the electrical forces. In addition, the volume of the container is much larger than the volume that the gas molecules take up. So we can neglect the volume of our real gas molecules. So once again, under these conditions of low pressure and high temperature, we can use the ideal gas law to help us describe the way that our real gas molecules behave. But if we increase the pressure to, let's say, 1000 atm from 1 atm, we can no longer use the ideal gas law to help us describe the way that our real gas molecules behave. And that's because of two important things. So at high pressures or at low temperatures, two things happen, two deviations take place. So deviation number one, the molecules are now much closer to one another. So our distance between any two neighboring molecules decreases. And that means the electrical forces increase and they're no longer negligible. And that in turn will decrease the pressure, as we'll see in just a moment. Now, deviation number two, the volume of the molecules is no longer negligible, and that's because when the pressure is increased, in this case the volume decreases, the pressure is increased, the volume that these red molecules, the volume that they take up is no longer negligible compared to the volume of the entire container. So, because of these two deviations, we can no longer apply or use the ideal gas law. So what exactly is the equation that we can use? This equation is known as van der Waals equation. But before we define what this equation is, let's define the following constant. So this constant B is defined as the unavailable volume of the real gas per mole of gas. So if we multiply B, the unavailable volume per mole, by the number of moles of real gas in our system, well then we obtain the volume that the molecules actually take up. And if we want to determine the volume of the empty space inside our container, inside our system, well, we simply take the V and subtract NB. So V minus NB is the volume of the empty space inside our container. So we must now replace V with V minus NB, where B depends on the type of gas that we are using. Now, what about deviation number one? So deviation number two was described in point one, and point two will describe deviation number one. So molecules are much closer to one another, and that means electrical forces are no longer negligible. So since we can no longer neglect attractive forces between molecules, each molecule will hit the wall of the container with less force because other molecules will pull on it. So before, under conditions of low pressure and high temperature, the distance between any two molecules was very high. And that means we can neglect the electrical forces. But now the distances are no longer large, and that means we can no longer neglect these attractive forces, and the molecules will be pulled to one another with more force, and so they will hit the walls with less force. So that means we have to also take into consideration what happens to our pressure. Because the pressure depends on the number of collisions, and the collisions with the walls of the container and the molecules is with less force, that means the pressure will also be less. So, let's begin with the ideal gas law. So this is the generalized law for ideal gas laws. And let's try to derive van der Waals equation from the ideal gas law. So we said that in this case, we have to replace the volume with V minus NB. So let's do that. So the pressure multiplied by V minus NB is equal to N times R times T. So in a real gas, the volume of the molecules must be taken into account. And that's exactly where this comes into play. So V minus NB is the volume of the empty space when we subtract the volume of the molecules. So let's take this equation and solve for the pressure. Pressure is equal to N times R times T divided by N minus or V minus NB. So notice I just said that because the electrical forces are no longer neglected, the force that the molecules will hit the container with will be less, and because pressure is equal to force divided by area, the force will decrease and the pressure will also decrease. So that means the pressure will decrease. So we have to subtract some value from this quantity to take that into consideration. So pressure is equal to nRT divided by V minus NB minus this constant, A divided by V squared divided by N squared, where V is the volume, N is the number of moles, and A is a constant that depends on the type of gas. So once again, in a real gas, the pressure created by the gas molecules is less. And so that's exactly why the pressure is less. We subtract this quantity here. So now, if we rearrange this equation, we get the following result. The pressure plus AN squared divided by V squared multiplied by V minus NB is equal to nRT, and this equation is known as van der Waals equation for real gases. So once again, under certain conditions, we can't use the ideal gas law to describe the way that our gases behave. Under conditions of a high pressure or low temperature, we have to use the following equation known as van der Waals equation.